So in the last video, we built a molecular orbital energy level diagram for hydrogen, and we used it to demonstrate why the diatomic hydrogen molecule exists, but the diatomic helium molecule doesn't. In this video, we're going to use molecular orbital energy level diagrams to answer a few other interesting questions. So many of you are likely aware that if a molecule is hit with high enough energy light, the bond can break. Why is that? Well, we're going to use our MO diagram to answer that question. So we have the framework for the hydrogen MO diagram already drawn out for us, but what it's still missing is the electron. So we'll start by adding those in. So over here on the left, I have one hydrogen atom, which has one electron. I have the other hydrogen atom on the right, which has another electron. That means we have a total of 2 electrons for our hydrogen molecule, H2, in the middle. So what happens when we shine light on this hydrogen molecule? Well, if the light has enough energy, we can excite an electron from the highest occupied molecular orbital, or HOMO for short, into the lowest unoccupied molecular orbital, or LUMO for short. And these are terms we're going to be using a lot throughout the course, because the most reactive electrons in any molecule are going to be the ones in the highest energy molecular orbital. And the most logical place to excite them, the place that's going to take the least energy to get there, is going to be the lowest energy orbital that still has empty space in it, or the lowest unoccupied molecular orbital. So let's see what happens when we excite an electron from the HOMO into the LUMO for the hydrogen molecule. I'm going to start by just flat redrawing my molecule, and then I'm going to edit the diagram to reflect the excitation. So 1 electron on each side for the hydrogen atoms, and 2 electrons in the middle for the hydrogen molecule. So if I excite 1 electron out of the HOMO, the highest occupied molecular orbital, which in this case is the 1 sigma orbital, up into the empty, or previously empty, 2 sigma star orbital, what has changed? Well, what has changed is the bond order. Let's calculate the bond order for each of these species. Our ground state, hydrogen molecule, and our excited state, hydrogen molecule. So the bond order for the ground state hydrogen molecule is equal to 1/2 of the bonding electrons, 2 of those, minus the 0 antibonding electrons, which gives us a bond order of 1. Bonding electrons minus antibonding electrons divided by 2 gets you your bond order. Well, this is consistent with what we would expect for a hydrogen molecule. When we draw the Lewis diagram for a hydrogen molecule, it looks like that. Single bond, bond order of 1. Perfectly consistent. Now, if we calculate the bond order for the excited state hydrogen molecule, we now only have 1 bonding electron. We've introduced 1 antibonding electron, and that means that our bond order for this molecule is 1 minus 1, or 0, divided by 2, which is still 0, which suggests that the bond has been broken. And this is why UV and other high-energy radiation can break bonds in molecules, because it can excite electrons out of bonding molecular orbitals into antibonding molecular orbitals. And if you move 1 electron from a bonding orbital, take it out, that drops your bond order by 1/2, and then move it into an antibonding orbital, that drops your bond order by 1/2 again, and the simple movement of 1 electron from bonding into antibonding orbitals drops your bond order by 1. And if that's a single bond, that's a broken bond. So in our next questions, we ask the MO diagram to tell us whether various ionic species should exist, because molecular orbital diagrams aren't only for neutral molecules, they are also for any polyatomic ions. So in our first question, we're looking at the hydrogen anion. Does this exist? Can we take 1 hydrogen atom and 1 more hydrogen atom And then if we have a negative charge, we add one extra electron. Does this species with 3 electrons in it exist as a molecule? In other words, will there be a bond? Or are we going to find that, like for the helium, actually the bond order is 0, so the bond never forms? So we are combining a hydrogen atom and a hydride ion. You can pick whichever one you want to put on either side. We have a total of 3 electrons as we counted them up over there. So that puts 2 in the 1 sigma MO. We still have 1 electron left over, so it has to go up in the 2 sigma star. So if we calculate the bond order for this anion, we have bond order equal to 1/2 of 2 bonding electrons minus 1 antibonding electron, or we have a net bond order of 1/2. So what does a bond order of 1/2 mean? Well, quite literally it means half a bond, or a bond that's half as strong as a single bond. So essentially, I guess we'll just say we would have a very weak bond. It's not a bond order of 0. We might be able to make this species, but it's probably going to be quite reactive, and it's very likely that it won't persist. So now that I've worked through that example for you, I'd like you to pause the video and work through the bottom example, and then when you're ready, you can unpause and I'll work it through it. So now that we're back, we're now looking at the dihelium cation. We know that dihelium, the neutral species, does not exist. It has a bond order of 0. What if we take an electron out, or what if we find some other way to combine helium and a helium cation to make this dihelium cation? Could that possibly exist? Well, we ask ourselves the same question. How many electrons are involved? So we have a helium atom, which has 2 electrons, and a second helium atom, which also has 2 electrons. This time we have a plus charge, so that means we're going to be removing 1 electron from the total because cations have lost electrons. That's how they obtain the positive charge. And so again, we have 3 electrons to fill in into our molecular orbital energy level diagram. So we had a helium on one side and a helium on the other side, but there's a total charge of +1. So we don't have the full 4 electrons. We only have 1, 2, 3 electrons in this cationic species. As you can probably predict, the bond order for this species is going to be the same as the bond order for the hydrogen anion was, because our calculation looks exactly the same. Our bond order is equal to 1/2 of 2 bonding electrons minus the 1 antibonding electron, or a bond order of 1/2. And that suggests that this species would have a weak bond, weaker than a single bond, but still some level of bonding interaction. As such, if we could come up with a way to make this that doesn't involve starting with neutral dihelium, we might be able to make it, but it would probably also be very reactive and not persist. And those are a couple of examples of the sorts of questions that you can answer with molecular orbital diagrams. Once we learn to build these diagrams for slightly bigger molecules, we'll look at some more questions.